Check.
So there is one more form that I printed out that you have to take sign after.
Okay, that's fine. We'll discuss this after we pass.
Okay. Okay. So good afternoon, everybody. Welcome to my defense talk. So I'll be talking about my thesis dissertation on data-driven performance optimization for wireless networks. So before I go into the details of the talk, I'll just try to focus on the big problems that we have today in mobile systems. One being connectivity. So we have problems with connectivity and coverage, and there is a lot of work to be done in order to make sure that mobile systems are well connected. We have the wireless network coverage everywhere. The next problem refers to experience in wireless networks. In the sense, there are different mobile applications that need to be provided with the right experience. For example, when we stream video in Netflix or in YouTube, we need to make sure that the video doesn't stall often. Or when we try to load a web page, we need to make sure that the web page loads in time. Right? So these are the different types of experience metrics that we need to optimize in wireless networks. And the third being energy. So there is a lot of applications that, for example, are energy hungry, and we need to make sure that the applications are running in an energy efficient way. So these are the type of three pillars that I try to visualize when solving problems in my dissertation. So the thing is that can we make things better? So yes, what I try to address in this thesis is taking a two-pronged approach. I look in the physical layer as well as the application layer. So in the application layer, I try to make sure that these applications that are running in these wireless networks in mobile systems are imparting a good user experience in whoever is using them. And I'm going to drill down about what exactly do we mean by user experience more objectively in the later part of the talk. And the second type of problem that we also look at is in the physical layer is how can I make the usage of the spectrum better? So as you know, wireless systems definitely depend on the availability of spectrum, and that is being used as like a real estate in communication. We need to make sure that the spectrum is being used in an efficient way. So the common flavor of the problem that I try to delve in is that I have a fixed set of resources. In case of physical layer, I have a finite amount of wireless spectrum that needs to be used among or shared among different communication technologies. And the other thing, we have like fixed network resources. I have a fixed amount of router space. I have a fixed amount of like capacity in the routers, or even the backhaul links as a fixed throughput. So given this fixed amount of resources, I try to build systems and collect measurements from these systems, and based on this measurement data, we try to figure out how can I optimize the system in a better way in order to harness better user experience, or in order to harness better bandwidth in the physical layers. So the other part that I also address in the physical layer is how can I do efficient localization in the network side. So the first two problems that I referred to is that how can I get better user experience in the physical layer. The second one, how can I make the spectrum usage better. And the third one is that in the infrastructure side, how can I make the prediction of the user's location in an efficient way. And how it can be used, it is very much useful for cases, for example, the cellular ISP might be interested in knowing the coverage map, right? So in order to do that, I need to know the accurate location of the user. And the other example is in the upcoming 5G massive MIMO systems, I need to do very accurate beamforming. And for that, I need to know the location of the user so that I can make the beamforming more efficient. So these are certain use cases where localization is kind of important from the infrastructure side, right? And I'm going to delve into like little bit about what I have done in the user experience side as well as the spectrum side, and then continue into more concrete details. So in the user experience side, one of the first problems that I deal with is how can I maximize the user experience among different devices running different heterogeneous applications in a certain network. And the other thing is that how do I make sure that I don't disrupt the performance of the other users who are already there in the network. So I need to fair to all the users, and at the same time I need to make sure that the quality of experience for a given user is maximized. And we cover different types of applications like video and web page loads and like VoIP users. The second type of problem that we looked into is comparing MVNOs and MNOs. So MVNO refers to a mobile virtual network operator. For example, many of you use Leica Mobile as some that's a MVNO that is under the MNO, that is the actual resource provider T-Mobile. So there are whether there are performance differences in between them. The third type of work refers to performance of heterogeneous media streaming sticks. We take an example of streaming video and we try to see whether there are performance differences for the same type of video provider and the same wireless network, still different streaming sticks, whether there are any performance difference in between them. So these 2 and 3 are kind of measurement driven. It's kind of taking raw measurements and trying to figure out why there are performance differences. And the first one is more of a resource provisioning problem in the network, trying to optimize the overall quality of experience. So this is the 3 different types of work that I have addressed in optimizing the user experience in a given network. The second type of problem that I look at it more from the physical layer perspective is how can I make the usage of the spectrum better? So what do we mean by usage of spectrum? So consider these are the 2 transmitters that are operating at a certain frequency f. And in order to make the usage of the spectrum better, what I need to know is that whether at a given location the spectrum is being used or not. So it is very much like you want to construct a building, right? Like, and you need to know whether at a given place whether there is a building that is already existing or not. So you need to know at a given location XY whether I have any signal power that is emitted at a certain frequency f. And for doing that, the state of the art is I have to construct a spectrum database that stores the spatial distribution of the signal power, right? So any given XY, I know what is the signal power. That's the intention of creating a spectrum database. So what is the use case? The use case would be something like at a given location, I need to ask that whether that spectrum is free. We also call it channel at a given frequency range. And the spectrum database tells me that whether it is free or not based on the thresholding the value of signal power. So it can be no, it can be yes. Now the basic problem that we try to address here is that how to create the spectrum database efficiently. So if you have some background about like wireless path losses, so one idea is that given the location of the transmitters, I can figure out using propagation model that what is the power at a given location xy, since I know the transmission power and the location of the transmitter. So what we can do is that we can populate the entire area for every xy, what is the signal power at that location, because I can use a propagation model, and given the location of the transmitters and their transmit power, I have a model to create this. What is the other extreme? So this is completely using propagation model, and the other extreme is that I can actually go to that location and take an actual sensor measurement. That also gives me the signal power at that location. So these are the 2 extremes. So if you look at the cost and accuracy, so the first one using the propagation model almost does not have any cost, because we are kind of dependent on a very few amount of data where I feed a propagation model, and based on that model I predict the signal strength everywhere. The cost is very minimal. This was one of the methods used for spectrum database that was proposed by Microsoft Research. The problem is that using one model everywhere sometimes gives a very poor accuracy. And we also have done measurements ourselves that show that propagation-based models are kind of inaccurate, and you lose a lot of spectrum opportunities. In the sense, when the channel is not free, it might say that the channel is free, or vice versa. And the other extreme that was proposed in a work by University of Wisconsin is you go and exhaustively measure everywhere, right? So that is not very cost efficient, because you don't know where to go and measure, and measuring everything as an exhaustive scale is not very cost efficient. So we try to come up with an way such that we can fuse both of these things, because we try to make sure locations where the propagation model does not work, we go and measure at those locations, and for the location where the propagation model works, we try to use the propagation model itself. So combining these 2 paradigms, we create something known as a measurement augmented spectrum database. So where we stand in between in this plot is we kind of still have a cost which is incrementally more than the model based approach, but at the same time we get a more accuracy compared to a model-based approach. Of course, it might be kind of less than the measurement-based approach because there you actually go everywhere and measure everything. So this is one of the contributions we have made. So if you want to do measurement augmented spectrum databases, you fundamentally depend on two types of locations where you need to measure and where you need to use the propagation model. So the places where we need to measure, I am referring as the yellow colored blocks, and what we have in between them are sensors. So if you need to do sensing at a very large scale, you need to have a lot of sensors, and the cheaper the better, because you need to do sensing at a very large scale. So I need to come up with a way such that I can shrink the form factor, probably crowdsource that spectrum sensing data. So what we created is something known as mobile spectrum sensor, where I can interface a mobile phone with a real very cheap spectrum sensing device, and we try to show that it is feasible to do spectrum sensing using these very cheap small form factor devices, and we also show that the performance in operating these devices are kind of within ballpark benchmarks. For example, the latency is not very high, or the energy consumption in doing spectrum sensing is not very high. The third work that we have done in spectrum usage is how to scale these things up in a bigger scenario. So when I have a lot of these sensors, how can I do efficient queries? Or how can, once you get this data from these sensors, I need to interpolate over a bigger given region. So how can I make this interpolation work better? Or how can I have a cloud-based system that actually uploads the spectrum sensing data, and based on that data I can do efficient channel allocation. So these are several problems that I have addressed here. Okay, so these are the basic three areas that I have worked on. If you have any questions, you can ask me. So the next thing that I want to focus on, why do I this is a research methodology, why do I delve into more of data-driven inferencing rather than analytical models? So I'll just consider an example here. Suppose you have a mobile phone that is streaming YouTube, and there are some problems in streaming the video properly, right? Now what do? This can be anywhere there can be a problem. There can be a problem in the access network. There can be a problem in the cellular core. If you are using a Wi-Fi, it can be like a Verizon Fios ISP, or you can go to Optimum. There can be a problem there. There can be a problem in the DNS selection, how sort of CDN is selected by your DNS, and there can be congestion in the internet. There are so many confounding factors that can actually play a role in order to make your video not stream properly, that hampers your experience. Now, if you come up with a suitable analytical model, it requires highly granular measurement probes. So you can actually model mathematically the entire path of the video from the CDN to your mobile device. However, in order to make that model work, you need to have measurement probes that are at a very granular level. You need to know, okay, what are the routers your packets are forwarded through, or what is the congestion level at each of these routers, or what CDN is actually selected, right? So this kind of becomes invisible, largely because this sort of system is kind of complex and non-transparent. I don't have access to a lot of information that is going on inside the network. At the same time, it is very complex. I don't know the exact routing path or what routers it actually goes through, right? So the type of approach that I take here is that measurement driven. I try to come up with different vantage points where I can take measurements. For example, in this problem, instead of using a single Wi-Fi access point, I can go to a different Wi-Fi access point, and using the same route for the rest of the internet, I can figure out whether my Wi-Fi access point was a bottleneck or not. Or I can simply change the device and try to see that whether my device was a bottleneck in streaming the video. Everything was probably fine. Or I can choose a different DNS resolver that gives me a different CDN server and try to see that whether my video would stream properly or not. This gives you kind of different vantage points where you can avoid this complex and non-transparent core of the network. So that is one of the motivations why I am trying to do data-driven approaches for inferencing network problems. So in today's talk, I will cover two kind of broad topics in my area that I have covered. One is how can I make better user experience in provisioning the network. The other type of problem that I have looked at, that I'll elaborate today, is how can I make infrastructure side localization better. So these are the two areas that I'm going to cover. Yeah.
What does the second part have to do with everything else you talked about so far?
The second.
The better infrastructure side positioning.
So the the better infrastructure side positioning, you need to, in order to have more information in the ISP side about say coverage, or you want to give better throughput by doing a beamforming, you need to know where the guy is actually. That helps the ISP. Anything else? Okay. So I'll go into the experience part of the talk, in particular one of the work that was recently presented in Connect 16. We call it as an experiential capacity of wireless networks. So it's a very complicated world of devices. I have a diverse set of devices. I have different types of applications and different types of heterogeneous networks, ranging from 3G, LTE, and in Wi-Fi itself has a lot of standardizations in case like A, B, G, N, and there is a recent AC. And people are also talking about 5G infrastructure. What is common from the end user's perspective is the quality of experience. So the quality of experience in all these applications matters a lot to the end user. As an end user, I'm not interested about what network I'm running on or what device. I'm basically trying to stream Netflix. I need to make sure that the Netflix video is running without buffering. That's what the end user metric is, right? So the basic problem here is that how do I provision this network? What do I mean by provisioning? I need to map an application in a device to a given network. I have a phone, I have a Samsung Galaxy phone that runs a YouTube application. I need to make sure which network to put in order to make sure that the user experience is maximized.
So that means you're assuming that all these networks are available at the same time, which may not be true.
Which may not be true. But at the same time, I can make a decision that whether I'm doing a correct job in admitting somebody to a given network or not. I can also see it as an admission control problem.
This will be at the cell tower.
Or based access point.
Or the access point.
Yeah.
Sure, but is that what you did?
Yes.
That is
what this work is, yeah. So in order to do this, what we need to fundamentally rethink is network capacity. So network capacity, in the sense how much of the load I can put into a given network, is known as a network capacity. So there are already existing metrics based on QoS that focus on throughput or latency. For example, I can have a 10 Mbps network, which means that the total amount of load that I put into the network, I need to make sure it does not exceed 10 Mbps. So this does not capture the characteristics of a lot of applications. For example, web page loads are very sensitive to delay, right? VoIP can be very sensitive to packet loss. So this does not play a role if I just model the network capacity in terms of a single QoS metric like throughput. The other type of approach that I talked about like several slides ago is a white box solution, or coming up with an analytical model of the entire network that also gives me a way in order to make sure that whether the user's experience is satisfied or not. So there I need to have access to all the network devices that is in the path of the packets, right? But however, these network devices are closed, and then architectures can change with time, and the set of equations that I have developed as an analytical model for the network needs to be updated, which might be impractical in many cases. So the approach here we take is coming up with a data-driven black box solution, which is inspired by doing a lot of inputs and outputs and seeing the response, how the network behaves in the face of different types of traffic mixes. For example, I have this Wi-Fi access point. What I try to do, I try to probe this network with different types of traffic mixes. I can have a lot of video traffic, I can have a lot of VoIP traffic, I can have a mix of them, and then try to observe the resultant quality of experience that is going on in the end user. So this is the basic idea that we are using in order to create this data-driven model. And using the response of this resultant POE as a function of these traffic mixes, I try to figure out what is the capacity model of the network. By capacity model, I just mentioned that how much the network can take into account, what kind of traffic the network can take into account, such that the quality of experience of the users is not hampered. So this is the basic idea that we have followed. So here there are two key challenges. The first one is that we need to track the quality of experience of the users from the network traffic. So that I need to do at the access point. And the second type of challenge is more intellectual here, is that coming up with a capacity model formulation for this new definition of capacity based on user experience. So we are not doing throughput based, we are not doing latency based, we are doing something that is based on experience, and that we need to formulate. So these are the two problems. So first I'll discuss the first problem of tracking quality of experience from the network traffic. I'll become more concrete about the type of work that we have done. Here we keep track of different types of flows. For example, I have done web browsing, video streaming, and video conferencing. These are the three types of applications that we have considered. And for each and every type of application, I have an objective metric that we call the quality of experience, or QoE. The page load time in case of web browsing, the video startup delay, that how much the video takes to load once you request and before it starts playing. And the other one is the video quality, that is measured in it's known as peak signal is to noise ratio. That means wherever the video is transmitted and wherever the video is received, what is the amount of loss that happened to that video frame, and that is measured as a metric known as PSNR. So these are the three objective quality of matrices that I am using, quality of experience metrics that we are using in order to track the experience of the user. So in Xbox, the system estimates this QoE from the network traffic, because in a realistic scenario, the applications might not report you back the quality of experience. So you need to detect it from the network traffic. So in our system that we built, we had several training mobile devices, and we have emulated different QoS scenarios. That means that we can have different types of throughputs that are being accessed by different users, different types of apps going on, and it can be natural depending on the dynamics of the network. So if it is running in a natural network, it is deployed in a natural network, people kind of switch on applications, switch off applications, and that creates the different traffic mixes. And based on that, for a given application type, in this example I show Chrome browser, so it's like a page load time. That is the QoE that we record here. And based on this data, for a given type of application, I measure the quality of experience as formulate it as a regression problem as a function of QoS. So this is again comes from the principle of diminishing returns, where I increase where this QoE is exponentially related to negative exponentially related to QoS. So once you add in QoS, initially your QoE becomes high, but as time goes on, the QoE improvement, the incremental improvement is not that high. So this is inspired from the IQX hypothesis paper that I referred. And once you have this model going on, being trained in the system, you can actually have devices that we call as test devices or real devices of people. So what we do for these devices is we take the quality of service from the network traffic. Here the quality of service refers to the throughput divided by latency. That is a metric that we use. So we look at the traffic, we look at the throughput, we look at the latency. From there figure out the QoS, plug that QoS value into that equation, and find out, in this example, what is the page load time, right? And just to show you a real example, here the orange points actually show the true page load time as a function of normalized QoS. I normalize the value of QoS because it depends on what the actual value of throughput is. And the black line shows the regression fit. And then we try to show that the amount of error we have is kind of minimum. And we did this experiment for different types of applications. We did it for video, we did it for web page load, and we did it for PSNR of a VoIP call. So we estimate the QoE now at the access point. So we know the QoE now, right? So the next challenge that I talked about is that coming up with a capacity model formulation. So here, capacity model is represented by this vector A, where A is equal to A1 to AK, where the AI represents the number of flows of a different class I. So if you have 3 video flows and I is equal to say 3, AI is the video, that metric is representing for video, so AI is equal to 3. So if you have 4 web page loads and that I is corresponding to web page, then AI is equal to 4. So like this, I'll give you an example. And the set of all A's that represents acceptable QoE by the network, we call it the experiential capacity region. So I'll give you an example to make it clear. So suppose this is a 2-dimensional example. I have only video flows and web flows that are going on in the network, and there is only one system, that is one cell phone that is connected to the access point at this current point of time. So my capacity vector here is 0, 1. So I don't have any web flow and I have one video flow. So 0, 1 is acceptable by the network, and whether it is acceptable or not, I am figuring out using the QoE regression model. So I can have more flows. 1, 1 it is acceptable. Say 1, 2 it is acceptable. Say here I have 3 video flows and 1 web flow. That might not be acceptable by the network. So the network says is like the QoE does not satisfy the network-wide policy. So this creates kind of a negative example for this network in terms of getting an optimal QoE for users. So I need to switch this traffic to a different access point, or don't admit this traffic in this access point. So once it comes back to a web flow, 2, 2 is acceptable by the network, and so on. So I can have this sort of points that tells me that whether this combination of flows results in an acceptable state or not. So all the points that are beyond this blue line are unacceptable QoE network-wide. So we don't accept those flows, or thus does not result in a network-wide good QoE. So, and the lower part of the picture where I have the green points, that we call as the experiential capacity region. So the collection of all the A's that result in a good QoE network-wide is known as the experiential capacity region. So we can accept those sort of metrics. So how do you find this boundary? That is the problem. Now this becomes our new definition of capacity region. So in order to find out this boundary, we have to use some examples, some measurements that we have done in the access point during learning the QoE and all. So we use these examples. So we put these examples in the Xbox system, and this Xbox system creates what is known as the capacity model. And in this system, we are using the boundary as an SVM hyperplane. So SVM hyperplane divides these two regions. Yeah, you wanted to say something?
So right now, where you have 2 dimensions vector,
Yeah.
right? How big this can be the vector? It could be 10 dimensions.
Yes. So in the actual work, we considered 3 applications, and I will come to that. And every application can run in different SNR scenarios. So it goes to 9.
And what is the complexity of finding this region? How do you find that? So given the vector of high dimensions,
Yeah.
how long it takes you to find the vector?
So it depends on the amount of data you feed, definitely. And we tried out different kernels in an SVM. So for the kernel we used is an RVF kernel, that is the simplest one. And for that it takes in order of like hundreds of milliseconds in order to train this.
So you're somehow finding what you're trying to do is in this space, you're trying to find some positive or some negative points. Of course, you're not exploring the whole space.
No.
Just finding positive, and you're finding a plane that divides them.
Yes.
Right. Okay. But then you're assuming when you do SVM that it's a plane as opposed to some arbitrary plane.
They call it like a hyperplane in multi-dimensional.
A hyperplane.
Yeah.
But still, it's still a plane, right?
Yes.
What makes you think it should be a plane?
It might not be a plane, it might be a curved surface
But
also.
then-
So it
so
depends
then
on the
arbitrary-
choice of your kernel.
Is there any intuition to believe that this should be? Well, it has to be somehow. There has to be some regularity, right? It cannot be arbitrary bunches
It
of
will be
islands.
a
It
convex.
cannot be bunch of islands, right? For example.
No.
The positive points, right? Cannot be.
No,
They cannot be.
they cannot be islands.
Why not?
Because if you think in terms of, say, number of applications that you need to support, there cannot be any discontinuity here. Because if you keep on increasing the number of applications, the throughput definitely keeps on increasing, the delay keeps on increasing.
So there's some monotonicity. That is,
Yes.
if there is some negative, if some vector is a negative, then if you increase any of the vector values, then that will also be negative, right?
Yes.
That's basically
Yeah. But in order to make it non-planar, we can use some other complicated kernels. But that is kind of a
No,
trade-off.
that's okay. I'm just trying to think that we can probably formulate some simple lemmas to actually formulate what kind of a division plane it could be. Whether it could actually be a plane or can be like, for example, any vector, if it is negative, then if you increase any value in that, it will also be negative. Right? That's one thing. Maybe there are some other things that you can formulate.
And that is probably enough to show it is a plane.
Really?
Yes, so we tried out something based on geometrical, like we tried out a convex hull based on all the exhaustive set of data points. But that does not seem feasible in like kind of multi-dimensions.
So we may be right that it may actually just imply that it's actually a plane.
Yeah,
I
because
don't
of the
know.
multiplicity, it doesn't be a plane.
To me, it seems that in general, the SVM method would actually, for a general problem, it can provide big islands, but probably for your types of problem, you will not see that.
So we actually looked at the exhaustive set of points,
Right.
and that from there we got that it is cleanly separable and there is no islands that
At
it
least for this example that you gave, I don't think. you
Even
see
for the
that.
actual example, like actual data set that we collected using from the test bed.
In principle, it's not a plane, it can be any.
It can be, yeah. There are other complicated factors like SNR and all. When you use that, it might not be a plane surface. So, yeah.
So the mitigation strategy here that you propose is stopping the client from connecting to this access point and selecting a different access point, right?
We are taking the responsibility of handing it off, yeah.
Right. So that requires for the access points to coordinate amongst themselves in some way, right?
Yes.
How is that coordination done? Because based on what you're showing here, it seems like this plane corresponds to all of these devices connected to
A single access
a
point.
single access point, right? And I'm not convinced that it's so nicely separable when you have two access points and any device can travel to any access point.
So, if these two access points are not interfering with each other, that is the assumption we have made. But as long as you are whether you can accommodate a given set of flows to a given access point or not can be done with this model. If not, you can hand it off to a different access point. But if these two access points are interfering with each other, then I have to create a joint distribution instead of having an independent model for each access point.
But even without interference,
Even without interference, I
there
don't.
could be imagine you have 3 clients
Okay.
and there is a nice stable configuration where everybody becomes a green point when 2 of those clients are on one access point and the third one is on the other access point, right? But you have to know which one of those clients has to be the separate one.
No, I didn't get your question. So you have like 3 clients.
You have 3
Two
clients.
of them connected to A and one of them connected to B.
That is the desired configuration in which everybody
Is
is
happy.
happy with the service.
Okay.
But how do you know which one of the 3 should be moved to the second access point?
Okay, so we are doing this admission control on a flow by flow basis. So whenever I have a network at a certain state at a certain point of time and everybody is happy, when a given flow comes in, the state transits to a different state, and I need to make sure that whether the state that it would be transiting to, whether it is acceptable or not. It might be that I can remove one other guy who is happy here to a different access point and accommodate 2-3 more guys here, but that's not the problem we are solving. That's more of a load balancing across the access points.
Is this mostly for an enterprise setting?
Yeah. So, for Prashant, we were also considering the actual vector that it looks like. We considered 3 different types of application, and we also look at the signal strength that the client is in. Because if you have 2 clients which have very good SNR, they both might have very good experience, but one of them having a poorer SNR can interfere with the fairness of for example, in case of Wi-Fi. So in that case, it might happen that both of them have a poorer quality of experience. Say both have poorer page load types, it might happen. So in order to handle that, we segregate clients not only based on the applications they are running on, but also we look at 3 levels of SNR. We discretized SNR into 3 bins. One is a very poor, one is medium, and one is high SNR. So this is the actual system that we deployed that was done in HP Labs. So we have a set of clients. These are running real applications, and we did this experiment in Wi-Fi as well as in LTE testbed. And we actually have a real eNote B where our phones connect to, and we run all permutations of apps that can go on in these several phones that we have connected to. So these are the different apps, the snapshots, that it is running a VoIP application or running a web page load, or it's streaming a YouTube video and it is recording all the instances of QoE that happened during running that permutation in that network. And we compare this admission control with several baseline algorithms that are in practice in the industry. One of them is that Cisco has in their router configuration is limiting the maximum number of clients. Like they make it hard-coded is that I just allow 50 connections to go into the router, 30 connections to go into the router, and they don't look at what throughput they are taking or what sort of activities they are doing. The other type of very common algorithm is rate-based, where I look at the maximum rate, that is the sum of all the throughputs that are being used at the current point of time, and that is being used for my admission control algorithm. So if it is 5,000 kbps or 50,000 kbps, that's a hard limit. Beyond that, I don't look at anything else. So we compare our approach with these two state-of-the-art algorithms, and how we kind of evaluate is that we have a vector of flows, that is the state of the network at a current point of time. So I have 2, 2 or 2, 2, 3, this is the state of the network. And we try to ask our system that whether I should admit this flow in order to, whether I should admit this flow or not. And if I make a wrong decision, that basically increases my false positive. So I need to make sure that whether I can admit the flow so that the overall QoE is fine, or don't admit. And we look at 3 different matrices. Precision is that the number of flows that are actually admitted by the algorithm, whether I have admitted any of them wrongly. So I admitted them, and then the network quality drops. So that is accounted as the amount of precision. And recall is that how conservative I am. So I might not be accepting somebody, but he could have been accepted. So that is focused in, that is represented by the recall metric. And accuracy is the overall correctness of the algorithm.
So what's your definition of whether the QoE dropped or not? Your threshold, you just say.
So it kind of depends on the network administrator's policy. So I can have median number of users should be happy. So I have a QoE per user. So I can have this thing like median number of users.
What did you use?
Median number of users were happy. So
and
I have
happy
means that if for every user the QoE is better than a threshold, and those thresholds are defined per
But
application.
that's hard to do, right? For example, if you do page load time,
Okay.
different pages have different page load time.
Right.
So you can't say that, oh, I'm going to do 5 seconds, because there might be a page that actually takes 20 seconds.
The granularity depends on, so your model's granularity has to be taken into consideration. What we did here is that we took several types of web pages which are similar in characteristics. At least the page load type distribution is within 5 seconds. And we made it like if it is more than 5, the user will be unhappy. So these are the charts that show the different
So, sorry, one more question. If you change the median to say 90% of the users are happy, did you try what will happen
Yes.
to precision accuracy? Okay,
Yes.
tell us.
I don't have the plots here, but we that is the threshold level we kind of changed. But if you make it very high, so the system will become very conservative. It depends on the policy.
Can I ask you a question? So how would you know, whatever you do, how do you know how close you are to optimality?
Optimality is kind of done here experimentally. So I know the entire feature space, where for every state I know whether it results in good configuration or not. So if I make a false positive, because I have the data, all the data already there. So when I actually make a decision, I can tally this with the actual decision that whether I made a false decision or not. That is optimal. Because optimal here is done by like empirically. So I know that whether this results in a proper good configuration or a bad configuration. And if I make a mistake, I can know whether I'm wrong or correct.
So you self-correct once you get a false positive means.
So the model is updated online. So we also try to make sure if the network changes. For example, I need to retrain the model. So I start from I train the model for a given network setting, And what happens is at a certain point of time, the network configuration changes. Maybe the SNR drops or the access point is moved. We try to see that what sort of sensitivity does it have with efficient controlling. So we show that Xbox actually catches up with changes in network characteristics. So if you see initially, the recall is very low, but since we actually have the SVM trading online, it keeps on improving with respect to time. So Xbox we actually shifted with Aruba's. Aruba is a company that is now acquired by HP, and that is they are being used in the client matching technology. They match which client should be talking to which access point, and they are using partially this algorithm. So I'll switch gears now and move to the next part of the talk. The next part of the talk is more to deal with accurate infrastructure side localization. So before going into the technique, I want to tell you what infrastructure side localization means. So you have a cell phone, and this cell phone needs to be localized in a given area, and using from the infrastructure side, from the network side. That means like T-Mobile wants to know your location. You cannot use your GPS. So what they do as a part of the protocol is I have the RSS. RSS means received signal strength value. So it is some power, say minus 70 dBm from these different towers. I have a cell tower that I am connected to that is known as the serving cell tower, and you can have neighboring cell towers at the same time. So as a part of the protocol, the phone sends out this information as a part of something known as measurement report, MR. So the measurement report constitutes of this information of which neighboring cell and what sort of RSS I am getting from those cells. And I have an estimation algorithm which estimates the location of the user. So x hat, y hat is the estimated location, and xy is the real location. So I can figure out what sort of error I have in the estimation. So why not so many sensors that are available? Because simply the network service providers don't have access to them. The protocols cannot have access to these things. And apart from that, I can have M2M devices, for example, which does not have GPS might be. Right, so unlike a lot of over-the-top applications, I don't have access to this sort of functionalities in a smartphone. The provider might not have. And the only way in order to figure out the location is to utilize the cell phone signal strength information. And at least in that some sort of RF characteristics that we can see from the cell phone coming into the base station.
So the cell towers today don't know how to localize you? I thought they were pretty good at that.
They use triangulation.
Yeah.
But the triangulation has errors that I'm going to come to. And there is one more overhead about training. So I'll see what is the focus of this particular work. So what they try to use, one of the state of the art is using fingerprinting, and I'm going to explain what does fingerprinting mean. So for every location x1, y1, I have a set of signal strength information that comes from different cell towers. So what they do is for a given location x1, y1, RSS-A, RSS-B, and RSS-C is like a feature vector that we need to record. And we do it for many locations. So x2, y2 for example, x3, y3 for example, x4, y4, and we can do it for a lot of locations.
So you're assuming that these are different frequencies, right? Maybe
No.
But that's also.
Same frequency.
If they're same frequency, how do you distinguish between the three different?
Sometimes they, not always, I cannot comment on whether it is same frequency or different frequency, sorry. But I just need to know for that given location what is the RSS. It can be different also, right?
No, if it is the same frequency, how do you know how much belongs to which tower? The problem you see is the total signal strength.
So it's kind of a different frequency. Sorry, yeah, it will not be the same. For the neighboring cell towers, it will not be the same. Sorry, I take it back. Yeah. Otherwise, it will interfere. So we have these three towers, and now based on this given region where I need to localize, I have this set of xi's, yi's, and at the same time I have a corresponding mapping to RSS vector. So once I have this fingerprinting database, I can have a test vector where the test vector looks like this. I have information from RSS A, B, C, and I need to figure out what xy is that I will get at x hat, y hat, right? And there are many deterministic as well as statistical techniques. So deterministic techniques in the sense I can simply use things like path loss, right? I know how the signal degenerates with respect to space. Using this data I can fit a model, and from that I can figure out what is the location of the transmitter. Or there are other techniques, for example, that depend on angle of arrival of that given signal. From that I can figure out which direction the signal is coming from. And there is of course things like triangulation. But
would an interpolation work here if the table is not very complete? That's basically the problem, right?
Yeah.
The table is not exhaustive.
that table is not exhaustive, and we make that is going to come to that. So
Shouldn't interpolation technique work also?
yes.
Basically, you interpolate at every other point, right?
So you can figure out the missing points
Yeah.
wherever there is no data, and you interpolate based on other that and predict what is the location. So it's kind of reverse interpolation because you need to find out the location from the signal string.
I'm saying don't do the locations, just interpolate at the missing points.
Yeah, then you need to do a lookup after that, right?
Yes, you always need to do a lookup.
Yeah. That is the kind of technique we are also using.
Okay.
So these have an accuracy of, so these numbers are reported with the industry that we were working with Huawei, and so they have a median accuracy more than 100 meters and sometimes more than 200 meters if we use triangulation. So here the focus of this type of problem, the main problem with this type of technique is we need to depend on a lot of fingerprints or these locations. And this number of locations is proportional to the cost. In order to do any reasonable fingerprinting, the cost of fingerprinting in a very dense way, you need to watt drive, for example, and this costs money. You don't get these XYs for free. So the cellular provider or somebody need to give some incentives to people in order to report their GPS locations, and that's how they do it. And this is proportional to money. So what if I don't have lots of these locations, but I have the feature vector there? Because this feature vector, whatever we said, is the ordered tuple of this RSS. This is free because the phone already sends it to the base station as a part of the protocol. So what matters here is I have a set of data points where I have the location fingerprints. Those are known as labeled data, and there is a lot of location where I don't have. This is known as like unlabeled data. Whatever Himanshu pointed out is there's a lot of locations where I don't have data. What do I do? How do I solve this problem? So our work is on minimizing this labeled data requirement. So see this scenario where I have these yellow points. These yellow points are as if labeled data, and I have a lot of these black points which is unlabeled. I don't know where they are coming from, but I know what is the value in that particular point. So this naturally creates a semi-supervised setting. So I have a lot of unlabeled data and some labeled data, and it creates a opportunity to use semi-supervised modeling techniques. So let's see what we can do with this unlabeled data. So I have a lot of this unlabeled data. I don't have any clue about what they are coming from. However, I know the feature vector because this is just an array of signal strengths, right? And suppose I apply unsupervised clustering. So in the signal space, they are clustered into separate buckets, right? So suppose these are the buckets. The orange ones is a different category of signal strength. The blue ones is a different category of signal strength. Based on that, I can come up with a clustering approach. Now, regarding the fact that I have a few labeled data points, I can anchor each of this signal cluster to a representative labeled data point. Because every labeled data point I have the XY as well as the signal string vector. And from that signal string vector, I can find out that which cluster in the signal space is very near to my labeled data point. And I can assign the value of that particular XY to that particular cluster. Right?
Just to clarify, so what you show now with these different colors, for the unlabeled points, these are actually obtained from the initial received signal strengths.
Yes. No location. So for a given physical location cluster, we say this is like say Li or L2 for a location cluster 2. And when a phone receives this, sends out this RSS 1, 2, and 3 or A, B, and C, my technique finds out the probabilities that it is coming from each one of these clusters. So given that this RSS A, B, C, this vector comes from location 4 is P4, right? And what we try to do is that we try to take a weighted sum of these locations weighted by the probabilities that they are going to come from this particular location. So sigma of LIPI or LKPK gives me the estimated location of the unknown data point. So I'll talk about a little bit about the semi-supervised modeling approach that we have used. We have used the assumption that at a given location the signal strength is a multivariate Gaussian that we have validated in the manuscript. It is there. So here the Gaussian is based on different cell towers that gives the dimensionality to the Gaussian and over a given location L. So f of s given L, for a given location L, what is the distribution at that particular location. And over all locations, because you have many locations, right? You have L1 to say L5. I get a mixture of these Gaussians. Every location has a Gaussian, multivariate Gaussian. For many locations, or n locations, I have n Gaussians that are mixed up, right? So whenever you get a data point, it can come off any of these n points, any of these n locations, and the resultant pool that it is coming from is known as a Gaussian mixture. So the learning problem that it reduces to, assuming independence, like Bayes' assumption is there, that what is the probability it is coming from a given particular Gaussian. I'll give a small example. So here I have a single dimension.
We have 5 to 10 minutes.
Yeah, we started in 210. Okay. So I'll give a simple example. Here we had like west and east. There are two locations and only a single dimension because I had a single cell tower. And how the overall data looks like is a mixture of these two Gaussians. Some of them are near to the cell tower, so it has a high signal strength, and some of them are far from the cell tower, so it has a low signal strength. So when you fuse all this data, it creates a mixture model of two components, right? So I have a few samples with level E or W and a lot of unlabeled data points that create the distribution. So once you separate out these mixtures, I'm going to say how we separate out. It is actually a resultant of these two red distributions. One is the left one, you see the Gaussian distribution for E, and the right one, the Gaussian distribution at W. So the black one is a resultant of these two red distributions. So the problem here is that given a test signal S test, that is a vector of just like a single number because there is only one cell tower, it is going to tell me that whether it is going to come from E or W, right? So it is going to come give me these probabilities. And according to our formula earlier, we just find out the expected value of the location by weighting them with the location as well as the probability value.
How do you decide how many Gaussians you have in the mixture?
We decide based on the we partition the space, and each partition is a component.
And a priori.
A priori. Yeah. So this is just an example. I give one example and skip to the rest. So if you have one particular data point RSS1, say the probability it is coming from east because the RSS is very high, sorry low. So coming from the east probability is 0.9. So it's a highly probable. It is far away from the tower. RSS value is very low. For a different point, it is mid in between. So I get two different types of probabilities, and we multiply the probability value with the location to get the estimated value of the expected. Same thing for a different particular point. To answer Peter's question here, we actually have a real data set which we collected overall in Stony Brook area, and we discretize this given region in blocks of 15 meter into 15 meter cells, and we made sure that distribution within this 15 meter into 15 meter square is different from a distribution in a different cell, right? And that's how we kind of come up with this number. What is the resolution of the grid? And at the same time, we need to make sure that we are not having too many components because that is going to take a lot of time in order to train the mixture model. So we had around 3K grid cells. We just considered the data wherever I have roads and buildings. We did not consider things like forest and all. So we had like 3K grid cells, and we collected 35,000 samples in the outdoor locations. We used T-Mobile's data. So we are using the RSS values coming from T-Mobile cell towers, and we used a Nexus phone. And we had kept aside 10K samples that were being used for testing the system. And how do you run this mixture model algorithm? We initialized each every location in this square as a Gaussian, and the mean and the variance came from the path loss model. From the cell tower, because we knew the cell tower's location and we initialized it in that way. Then based on that entire data set, we run the EM algorithm on that data. That EM algorithm basically finds out the mixture probability distributions, and that is my learned model. So whenever there is a test data, I need to predict the location of that particular test data. I predict it using the learned model, using the algorithm that I told earlier by weighted probability distributions. So this is the value of median accuracy is approximately 70 meters. When we use the red plot, that is a mixture model one. And apart from that, there are certain classical techniques that people have used in literature while looking at statistical localization techniques based on Gaussian F base is one and k nearest neighbors is the other one. This is just using 10% of the samples. And with 1%, we kind of reduce the amount because our target was to minimize the amount of level data. So when we use just 1% training samples with levels, the median accuracy is still less than 100. It is 90 meters across the Stony Brook area of like approximately 3 square kilometers. So there are certain observations that we made. We saw that if we input more and more unlabeled data, the system's performance improves. This is interesting because whatever we are providing is not labeled data to the system. So I don't have labels, just unlabeled data which is available for free is making the system better and better. Up to a certain extent, because it cannot get infinitely better. That is a certain number known as the base risk, where the performance of the system is limited to the variance of the signal itself. So we cannot do any better than that. The second observation that we made was that the high error regions are very clustered. So there are certain regions, this is near the hospital building, there is something near the playground, wherever we have these high error locations, and they are very much clustered. And we used a metric known as Moran's-I that gives you a measure of clustering. The good point here is that I can actually use more dense sampling or collect more level data in those locations.
Any intuition why those error-prone things are clustered together?
Because this is a hospital. So in the hospital, what happens is there is a building, and then it causes obstruction to signal path loss. So it's very much unpredictable in comparison to places wherever there are like smaller buildings and flat terrains.
So could the result be an artifact of the region, the shape of the region, or the propagation model?
The accuracy is an artifact of that.
So then you're saying your confidence is low that if the region were to change, the accuracy remains similar or equally good.
Yes. So if you have more, like in Manhattan, this might not work with this amount of data. You need more unlabeled data in order to come up with that.
So is it true that if you have infinite amount of unlabeled data, then you'll actually get very good accuracy?
Up to a base risk. So if the signal fundamentally fluctuates with this variance, then you cannot distinguish in between two places.
Okay, if you have let's say unlabeled data for every point in the region, let's say, but we have some number of labeled data. I don't know how much. Can we get 100% accuracy? No, right?
No, so accuracy cannot be like 0 meters. So there is already a variation. And now if the region is very complicated, the variation is more.
Okay, so I guess the point I'm making is, can you give me an example of data where accuracy could actually go to 0 meters? So, one example is, if you
So
have
wherever you
labeled-
don't have any shadowing, it will go to 0.
No, I'll give you an example. One example is, if let's say you have labeled data for every point in the region, then of course you can get 0 accuracy, right?
Yeah.
0 meter accuracy, right?
Probably no. So it depends on like if you have one level data point, it's a sample of that particular distribution, right? When you retake one more
Okay.
sample, it
Okay,
will not be the
noise.
same.
Okay, yeah.
It will be confused.
There is a noise, okay. Okay.
So one more thing that helps us here is like what is the impact of cell tower density. So in Stony Brook area you have a lot of variations. There are certain places where it's very much covered under different cell towers. I see as many as 6 neighboring cell towers apart from where I am connected to. There I can get to almost 40 meter median accuracy. And overall it was 90, but even if you look at locations like Manhattan, wherever there is a lot of dense deployment of cell towers, I can have a reasonable accuracy with this sort of technique. And the beauty of this technique is that I am not using level data.
What is the intuition behind it? Because if you have
Your feature
pairs,
vector is teacher.
the clusters are only more, right? There are more number of clusters, right? And
No, the cluster number is dependent
okay,
on
okay.
the
So
breakup of the
dimension
region.
of the vector is
Increases.
okay.
So I'll summarize. So we minimize the amount of level data requirement. Here 1% of the level data we were able to achieve approximately 90 meter of median accuracy, and we extended it. I am not covering it in this talk. Is completely unsupervised setting where the level data is coming from a proxy of path loss. At a given location, I know the level of that location because I know the GPS coordinate of that location, and the initialization was just based on path loss. So you can go to 100% unlabeled data in order to solve this problem. Of course, you are not going to get 90 meter median accuracy. You got something around 130 meter median accuracy for Stony Brook area. So I'll conclude. So these are the thesis contributions that I have made. First one to do with the different problems in the user experience space, where I can have two flavors. How can I optimize the POE of a given user in a given network setting? How can you provision the network? And there are like two measurement studies that we have done in order to understand the performance differences in different systems. The second one is the spectrum usage, where I actually developed a measurement augmented spectrum database. And in order to make the spectrum sensing more scalable and feasible, we developed mobile spectrum sensors and did a large scale deployment of that and studied the efficiency of the system. And the third one is what we just now described, is the infrastructure side localization. So with this, I would finish my talk and I can take more questions. So these are the different people that I have worked with, both PhD students, professors, as well as master students. I thank them gratefully for helping me in my thesis. Thank you.
All right, do you have any questions?
Can you explain, for the last part of the talk, when you have labeled data and unlabeled data, so you have measurements of the unlabeled data, and then these three RSS values should be enough to provide an estimate of that point where the measurement. That's an estimate. Of course, it's not perfect. Then how? So the question is, how do the labeled data help improve that estimate?
Here the unlabeled data, whenever I am dealing with unlabeled data, the unlabeled data does not have any clue where the data came from. So it helps in order to anchor that signal cluster in a given physical space.
So who's doing the estimation? Who is estimating here? Who is localizing?
Who in the sense?
Who performs the localization?
The infrastructure side, there's some algorithm running there.
Right.
That has a mixture of both unlabeled as well as labeled data.
Now I understand. So let's say that there is a phone that collects these three RSS values,
Mhm.
right? And then these values are sent to somebody
To the provider.
right. And then the provider doesn't know where these signals come from.
No. They have to find out an estimate in order to guess his location.
So now they do this clustering the way how you described, meaning that they'll put in particular parts of your space, and then so in other way you sort of deduce or make an inference or guess where they come from.
Yes.
So now you can localize these.
Yes.
So now, so what you're saying is the labeled data only help in clustering these initial values of to basically put these localized objects in parts of the space so that you can actually
In parts of
localize
his
them.
geographical space.
That's the only place where
Yeah.
you
Yeah.
use them for.
Yes.
Now, given that they're there, do you think you can use now those because you believe the labeled data to be of very high quality?
Yes.
So, do you think that they can be further used to improve the locations of these unlabeled data?
We are already using that in order to
The first
build the
But
clusters.
as a follow-up, do you think you can use them sort of in an iterative way?
So we are using this EM wherever we are iterating over, like I first make a guess and then make the guess better, and so unless it
I think what
converges.
Peter is trying to say is that when you are using unlabeled data, if you localize this unlabeled data,
Already, yeah.
I can't localize unlabeled data, right?
you can, right? Because you are localizing test samples, so you can localize all unlabeled data based on unlabeled data.
Yeah, so that's a different thing. But when in a real setting, when you have a lot of unlabeled data, you don't know what to do with that.
In real setting, you have labeled data,
Yeah.
and you have unlabeled data. You can treat all the unlabeled data as space-based and localize them.
But I don't know whether it is adding any more information to the system.
No, it doesn't. It's just a different.
Yeah, so I will not think that it is, like intuition is not going to get better. If you are getting more labeled data or more unlabeled data, both are going to help. So
Basically,
one
what I think
idea
is-
I can think about is that you probably need a threshold amount of labeled data in order to make the system work, and then you can have more labeled data in order to make final improvements. So if I have a threshold on error that I need to have at least 100 meter of median accuracy, I can figure out a way in order to get, I need this much amount of data, this might be the density of labeled data, that we can come up with.
So for now, let me further probe this. So for now, what you do is you get certain amount of labeled data, and then you estimate the locations of the unlabeled data.
Mostly doesn't do that very
But the system does, no?
well. No, he's doing semi-supervised learning, right?
So if
it's
I
not-
go to the actual algorithm, no.
So using the unlabeled data also for training.
Yes. So,
It's not-
so here the step I showed
Yes.
was that you have these black points.
Yes.
That so this particular stuff, this is clustering not in the field. I'm showing it for the like understanding purpose, but these red or blue and these green things has nothing to do with locations. These are doing it in the signal space. Now I don't know where these blobs will go to in the physical space. I need these yellow points in order to guide these blobs to a certain point in physical space.
Yes.
So there these yellow points come.
Yes.
So yellow point ties this blob to somewhere in the ground.
These yellow points are the labeled data.
Level data.
Exactly. So now, at the end of the day, what do you know about these other points?
Sorry.
At the end of the day, the system, what does it know about these other points? Does it know where they are located? Does it know the rest?
Know about the yellow points.
The yellow points it knows, they're labeled data.
Yeah.
What about the other points? Once you finish all the estimation, EM algorithm and so on, does it have estimates for these, the system?
For my work, I have ground truth data. I know the location.
No,
of
no, what he's
But he's
asking
not-
is
that's not.
the unlabeled data, after all the training that you have done, on the unlabeled data, what can you say? Do you have the precise, do you have the location estimates for them, or you just know which cluster it belongs to?
I have a location estimate for them.
Okay, so now, this is what I was doing. So now, what I was aiming for. So now we have these other, so you have very good knowledge about these label data, where they are, but you have approximate values of the locations of the remaining points.
Yes.
Do you use these estimates for the following points that come, that
Yes,
need
for the
estimation?
test.
Okay, no. So because I use this EM algorithm on this entire set of data to create the model. Now the test data we don't use anything here. So
Right,
what?
now he uses the,
Some other data.
Alright, so all the time you only rely on the label data.
Labeled and some unlabeled, but we are not using the unlabeled data for testing the system.
the
So
question
I didn't mean for the testing, but for the estimation, for localization.
So that is the test data that we are using for estimating the location. So I have a bunch of data points. So suppose I said 35,000 data points. Out of that, I just have labels for only 1% of them,
Yes,
and rest are unlabeled. Now I take this data, put it to the EM algorithm,
yes.
and tell it to create say 10 clusters.
Right.
It creates 10 clusters.
Right.
Now I have the learned probability distribution for every cluster.
Right.
Now there is a separate set of data points, not out of the 35,000, separate set. I use each one of these points in order to plug it to the EM, and the EM tells me what are the distributions of soft probability that is going to come from the different distributions. So I don't touch this for testing.
But I was aiming at, my question was about what if in the real now setting, you want to really do localization of new objects. And then would you use the already estimated locations of previous objects to improve the future estimates? That was my question.
I see.
kind of discussed this. This is
I
active
don't
learning
know
or-
whether it is, yeah, so.
Because
then-
you can certainly measure how accurate you are with all these estimates, and you have to take
But you
that
can
into
go
account.
completely wrong in the way if the system is not learned enough, if I'm using the new proxy, the new estimate as new level data points, if I am wrong, I might go in the wrong direction. So if the system, we can kind of know that the new learned model is kind of
There are
right.
ways to test it, so don't worry.
Huh?
There are ways to test it that if you are becoming unstable in
Okay.
your estimates.
Yeah, I have not investigated that.
All right.
And also, so just another comment, like for example, when I ask you about how you do
Discretization.
the basically the partitioning of the
Yeah.
space, I don't know if it would work, but probably it would work, but I don't know if it would be useful, is to use methods that, again, data-driven methods that tell you how many mixins you have. You don't have to design it
Yes.
yourself, but you
Initially
design
we
it
did
yourself.
that. So we use something like this AIC and BIC in order to figure out the number.
Not like that. With ASC and BSC, you still have to assume maximum number.
Yeah.
With this, no, you don't assume anything. You can have as many different classes as you have data.
So is it like
These are
something like
non-parametric methods.
k-means clustering I keep on doing in order such that for a given value of k something is minimized?
This is actually an excellent application for something called directed process-based methods for deciding how many classes you have. And these are non-parametric. And why I say it's excellent because your number of actually data can grow with time, and then it's meant to work for these type of applications. Something like that, I don't know.
Yeah.
You don't tell us about future work, but it depends on what you're going to do.